Hello everyone and welcome to my channel. In this episode of EVM programming course, we will take a look into working with bytes. In the previous episode, we were talking about opcodes, and this episode extends this information about working with low-level bytes, which is what opcodes do. So let's dive in. So first of all, what kind of byte operations do we have inside of EVM? Those are like bitwise operations like AND, OR, XOR, NOT, and all those shifts like shift left, shift right, signed shift. We have comparison operations, lower than, greater than, not, equal, is zero, and arithmetic operations like addition, multiplication, division, modulo. And we'll go through them, but let's first start with the lowest level thing, which is like the basics of byte manipulation. So remember that last time when we spoke, I introduced you to different kinds of representing the numbers, and we were talking about hexadecimal, decimal, and binary. And this will be super helpful right now because we will use the binary notation to understand how the byte operations really work. So I have opened Bitwise command, which will be super helpful here. And let's start with this number. This is number 1 in binary, and this number actually can be represented as 1 1, which in binary is 3. If you don't remember how binary and hexadecimal really works, please come back to the previous video when I discussed that. So as you know, EVM works on low-level bytes, and it lives and breathes and only does that. So in order to really have deep understanding of how EVM works, we first have to understand how the byte manipulation is working, and then we'll move on to some more advanced topic. As I showed in types of operations, first let's start with bitwise operations. So those are operations that are allowing you to modify the number by performing operation on each of the bytes. So let's start with a simple bitwise OR. It slightly differs from the OR that you may know from Solidity because it does not operate on the whole value, but it operates on each of the bytes separately. So you can think about it as an OR, but it performs not one operation, but it performs the same operation on each of the bytes separately. So in this case, as you can see, we have this number 3, which is in binary notation 1 1, and we are having bitwise OR with 0. That means that it will be 0. But for example, if we have two of these numbers, 8 and 3, if we perform bitwise operation, you can see here that we are comparing this number in this notation to this number. And what this bitwise OR will do, it performs OR operation on each of the bytes. So 1 or 0 is 1, here the same, 0 and 0 is 0, and here in the first number it's 0, but in the second number it's 1. So the result of that is 1011, which results in 11 in decimal notation. Now, what if we change the sign to the bitwise AND operator? The results are quite different because, as you remember in Solidity, AND only works if two sides of the equations are equal, and in bitwise operation is the same, but for each of the bytes. And here 1 and 0 equals 1, the same here, and here. So in order to have some bytes successfully pass this check and set up to 1, we need to have 1 on both of those numbers. So in case of this number, 3 and 10, which has this notation in binary and this in hexadecimal, because only on this position we have 1s on both of them, the result is also 1 on this particular position. Okay, let's see how other operations work here. Maybe let's go with XOR. So this is how you annotate XOR in bitwise operations, and XOR returns 1 only in case of two numbers differing in specific bytes. So in this case, 1 and 0 is different, so we set 1. 1 and 1 is the same, and 0 and 0 is the same, so we set 0. And again, those two numbers are different, so XOR will give us 1. So the result of this operation in this notation in binary 0x9 in hexadecimal and 9 in decimal. Now I will slightly change those numbers because we'll do shift right and shift left operations. In this case, we have this number, which is 3 in decimal, and we shift it to the left by 0. So of course, this is still the same number, but what if we want to shift the number by 1 byte? You can see that before we had like 0011, and after these operations, all those numbers were shifted left, and the resulting number is 110, which is 6 in decimal. When we shift it by 2, you can guess it, the number we are having is 11 and added 2 zeros. So shift left always adds zeros to the right. So you are taking the number from its position and you are shifting the number, and what is filled in the previous positions are zeros. And of course we can shift it by some bigger number. And now question to you, how do you think by shifting this number by 8, what will happen? The answer is simple. You are shifting everything to the left, and like all those numbers are filled with zeros, so you're ending up with number 768 and 300 in hexadecimal. Now, apart from shifting left, we also have shifting right, which will do the opposite to the shift left. It will take the number, shift it to the right, and fill everything what was there before with zeros. So in this case, we had like 0011, we are shifting it by 1. So what we are ending up with this number, like this is discarded, and we are adding 1 number. So our resulting number is 1. The last bitwise operation we have is not. So in this particular website, it works slightly differently because it accounts for negative numbers. But normally, if this number, this not bitwise operation just flips all the bits. So this number 0011 will become 1100. In binary notation. And here it's a bit different because, as you can see, it treats it, of course it flipped all the bits, but it treats the last byte as the negative number signature. But if we didn't account for negative numbers and just kept it off as plain bytes, we are just flipping the byte to the opposite side. Oh, and one more thing concerning the negative numbers. In case of EVM, you also have signed right shift. So it allows you to shift bits for the numbers that you are expecting to be negative. Next one, we have comparison operations, and we'll move to the EVM playground for that. Let's push 2 numbers. Okay, and let's first go through lower than. So we are pushing 2 numbers, and we can actually use different opcodes to push more bytes. And when you run it, we have 1 and 2 on stack, and then we perform lower than. And what we end up with is 0. 0 always means false in byte operations, and non-zero, like 1 or whatever other number than 0, means true. Why was it not lower than? When we push 1 and then 2, like we will have this first number and this second, and the lower than compares if this number is lower than this number. Cool. And now what if we change the sign to greater than? Push and greater than, and as expected we have 1, which means true. The same goes with equal and others, and how they are all useful. When you, for example, compare something, you are checking some condition, like if one number is lower than second number, perform some action. Okay, so how it translates to the low-level code. So imagine the situation. I made a random jump test just to show you that we have our code block, and this operation, which is just executing the if statement, can be translated low level as pushing the 2 numbers. So we can run it and see. Then we are checking if this is greater than, and of course it returns 1, which means true, that 2 is greater than 1. We are pushing, in this case, because we are preparing our jump, we are pushing the process counter to which we want to jump, 0 in our case, and jump if will jump to the first element from the stack if the second number is non-zero. When we call it, yeah, of course, we moved here again to jump test, and actually we created ourselves an infinite loop because it will go forever. But actually this is how you translate the high level Solidity code to low level EVM. Now I'd like to quickly show you how the other low level bit operations differ from what you know from the high level Solidity. For example, not, it does not just check if something is true or false. On the bit level, it just flips everything. So for example, if we push this big number and then we are flipping it, what we are ending up with is this number, and in the places where we have ones, it just flips. Okay, and there are also the signed less than and greater than. The only difference is that they account for the number being negative or positive. And actually, if you are not sure how the specific opcode works, what you can do is to visit the official Ethereum specification, because for quite some time now, the official EVM specification is written in Python. And if you want to create your own EVM implementation in whatever language, you have to make sure that the code works absolutely the same how this execution spec. So for example, for operation greater than, we are popping 2 elements left and right from the stack. Of course, we are charging the gas, and as a result, we are converting to number. If those two are different, then we push the result to the stack and increase the process counter by 1. As a side note, you will always see this pattern. First, we are getting the values from the stack, then we are charging gas, performing the operations, push the result to the stack, and finally increase the program counter. Okay, and I would like also to go through this one additional opcode, which is E0. All it does, it checks if the first value on the stack is 0. Given this program, when we run it, of course, after first push, we have this number on the stack. Of course, it is not 0. So the stack returns 0. But when we perform it again, our stack, the operation took the 0 from the stack and returned 1 because the first element of the stack was 0. When it is useful if you want to flip some condition. So for example, if you are checking for some condition, for example, number A is bigger than number B, but you are negating it. So it's super useful because this is0 is actually the equivalent to the negation in Solidity. And finally, we are landing into arithmetic operations. So, well, they work just as you can imagine they work. But in case of sub, remember that the order matters. So it will be subbed in reverse order, because after those 2 pushes, first is this element and second one is the element here because of the stack value. And what do you think? What will happen if we remove 500 from 500? Normally, maybe you remember that it will just silently underflow. It will flip all the way down to this number. So that's why this is very dangerous. It was solved by Solidity 0.8. So in case of Solidity, you have additional checks if after this operation the number is correct. However, this Solidity has to add additional opcodes just to verify if the number didn't underflow or overflow. Okay, next is division. Of course, due to precision loss, this number divided by this will not be a fractional number, but will be rounded down to 0. But now, what, for example, if we have like negative number, which is depicted here, so this is actually minus 1023, but now, what if we have signed number and we want to divide it? So for example, dividing it by 9 will give us this number. So this is really bad because, as you remember, the negative numbers start with all F's and then go down to mean the higher number. But here what we are ending up with, it's not minus 1023 divided by 9, which should be like really small number, but it divided this number as if it was the positive number. So if we have signed number, we should use the signed operation like signed division, signed modulo, and others. So yeah, like in this case, it's actually accurate. Now, those are just the building blocks. And now we are using those small blocks to build bigger and more complex logic. And in order to do that, we need to manipulate the bytes. So the types of byte modification that we may have is like accessing the specific byte, bitwise shift, bitwise operation that we mentioned, and or XOR, and others. We also have concatenation, which just means that we are joining multiple byte sequences together to create a bigger one. We have slicing it and splitting into smaller parts, which is the opposite operation. Then we have length operations to check how long something is. We have type conversions between, for example, uint 256 to uint 64 or to address or any other type, basically. We have data packing and unpacking. So this is what, for example, ABI encode and code pack does, and hashing. And I would like to quickly go through and show you how EVM does specific things which are not seen on the high level. So for example, let's imagine that you have some struct that has two fields, uint 258. Okay, so let's imagine that we have this struct, and when it's stored in storage, this is tightly packed. So how it's really performed by Solidity? So basis of our conversion will be the mask and those two exemplary numbers. So let's say that our A value of extract is AA and our B value is 1, 1. So this is what we will be using. So first of all, what are byte masks? Byte masks are super useful in case that you want to clear some values. So let's say that we have this 32 bytes value that we want to mask the upper bits from. So let's say that we want to, for example, typecast this 32 bytes value to only 16 bytes. So you are preparing this mask and then you are doing the bitwise AND operation. And because AND only sets the bits that are present in both of the values, and we are only setting first 16 bytes to one value, we will end up with everything above this mask being zeroed out. So if we run it, first we are putting this mask, and oh, you can see here that all these zeros on the beginning was just trailed. So they are there still. Everything is padded from the left with all the zeros, but for the brevity, initial zeros are not added here. And then after execution, you can see that we have this number that is only half of the size. So our result here is that we caught only this. But what if, for example, we wanted to mask out and get only the upper bits? I will now change it to A's and B's so that you have like better understanding. Of course, OR will not work because the A's will still be here, and this won't work because it will be all the F's. Yeah, so you can see that because it was 0, so 0 or all the A's gives us A's, and F bitwise or with B gives us F's. So how can we do that? Well, this is actually very simple. We just have to add additional opcode, which will flip our mask. Remember that Bitwise not operation flips all the bytes. So after the not operations, our all zeros and F became F and all zeros. So now our mask will work for upper 16 bits and lower 16 bits will be set as in the second number. Okay, so let's try it. We push our big number all 16 A's, 16 B's, and after execution you can see that of course we have our mask worked because this is all zero. But what if we wanted to have this number, you know, not as this big number, but we wanted to diminish this number to be like only A's? So the answer is simple. After this masking operation, what we can do is pushing the amount of bits that we want to shift and shift it to the right. So when we run it, here we flipped our mask. Then we are pushing the number that we want to mask off. Okay, we have our mask here applied, but now we want to move it 128 bits to the right, which in hexadecimal is 80. And after shift right, we are getting back the number that we want. This is the basis of how the data conversions operation work. And actually this is the same how the, for example, splitting and slicing works. You are getting just a part of the value, you are masking off everything else that you don't need, and you are left with the number. Concerning concatenation, you are not doing any masking, you are just putting together values one after another, probably using memory, because as you remember, if you are using memory, you can use extended amounts of consecutive slots. This is all that I wanted to show you today. I hope you learned something new, and see you in the next one.